Around and around and around. Hi, I'm Bob McDonald, and we're here at Science World in Vancouver, and this is a model of space, where things just go around and around. Also, objects in space tend to be round. Can you guys name me anything in space that's round?
The Earth.
The Earth?
The Sun.
The Sun?
Jupiter.
Jupiter?
The Moon.
The Moon? Planets are round, stars are round, moons are round. On this program, we're going to find out why and why some things are not so round. So keep your heads up and stick around. Get it? Stick around? Yeah. Look at anything in space, and what do you see? Something round? All the planets are shaped like balls. So is the sun and all the other stars in the universe. The planets all go around the sun in round orbits, and the sun itself follows a circular path around the Milky Way galaxy. Everything seems to be round. There's a force out there making them that way, the force of gravity. It's hard to believe that we live on a round ball. Makes you wonder why people on the other side don't fall off. Well, they're probably wondering the same thing about you. You see, everyone on Earth feels the pull of gravity, and gravity always pulls towards the center of our planet. So it doesn't matter where you are on the Earth, you feel a pull towards the ground, and it makes all of us feel like we're the ones on top. In fact, there is no single up or down. Each one of us has our own personal sense of where down is, and we're all right. Down is simply towards the center of the ball. Okay, I've got a really dumb question for you guys. Where is down? This way, of course. We always point to the floor when we say that is down. But you know, if you go down far enough, right through this floor, you're going to come out the other side of the Earth, which is kind of a funny thought. But when you think about it, we live on a ball, right? And right now, we are in Canada, which is here. So we call down in this direction. Can anybody find any other countries on this globe? China? Okay, up, there's China. Okay, here's China. China calls down this way compared to Canada, which is over here, calling down that way. Any other countries?
Australia.
Australia. Okay, Australia's under here. They call down in this direction, while China calls down in that direction. Anybody else? Africa. Here's Africa. Boy, Central Africa, right into the equator. They call down sideways like that. Any others? What else we got? Well, anyway, the point is, all of us are pointing in different directions. Everyone on Earth, when they point to down, they point to the ground, but they're all pointing in different directions. Where are we all pointing? Where's the ultimate down? The core, the center of the Earth. We're all pointing towards the center of the Earth, and that's why the Earth is round. It's really trying to get as small as it possibly can be, and the smallest shape you can get is a ball. Here's another way to look at that. I've got some modeling clay here, if you guys just want to take some of these pieces. Now, these pieces that we have are very irregular. Let's see if we can make it as small as possible. Try to make this clay as small as you possibly can. If there's a piece sticking out, you push it down. Try to get everything towards the center. Make it as small as you possibly can, and if you just keep working at this, make sure that nothing is sticking up, everything is down. Ultimately, the shape you're going to get is what? What do we all got? Yeah, a ball. In space, this force that pulls everything towards the center and makes things round is called gravity. In fact, gravity always pulls towards the center of an object, no matter what it is.
So stars and planets are round because they're molded and shaped by gravity, one of the four fundamental forces in the universe. And gravity isn't very strong, but it acts over tremendous distances, and it's extremely persistent. Over the history of the universe, it's constantly working. And gravity is kind of democratic. Imagine that when the Earth was young, and I just happen to have this on my desk, handy for an astrophysicist. When the Earth was young, it was still molten. It wasn't solid yet. And the Earth has a molten core now, but at one time it was all liquid. And so it could flow around. And imagine for some reason it started out in a regular shape like this. Now gravity always works most effectively where there's the most mass. So if you were, say, standing on the surface of this really irregularly shaped thing that had all the mass of the Earth, here you'd feel a lot lighter because there's not as much stuff underneath you as you would here or here, where there's quite a bit of material underneath. And so gravity is pulling more effectively in that direction than in the other, and it's naturally trying to compress this stuff. And eventually, it will compress it into a sphere. And gravity does a much better job of this than I do.
Now, this whole idea of gravity pulling things together into round shapes has to start somewhere. And I can show you that using my beautiful garbage can gravity well. I'll show you how to make one later on in the program. But it represents space. Now, if you take just one object and you put it out in space, it'll just sit there. But you can see that it also dints the plastic a little bit. It curves space. Einstein calls that a gravity well. Now, one object isn't much, but if you add more objects to it, or you put two beside each other, they will be attracted and they will come together. And the more you add, the more mass you get. And since all objects have gravity, the more you put, the more gravity you get. And you can see that they all start to come together. And eventually you end up with a shape that is, well, more or less, generally round. And the gravitational field has gotten bigger because large objects have more gravity than small ones. But that's how you form moons, planets, and stars. They're all made the same way. That's why all the planets appear in our telescopes as round balls. Or are they? Let's take a closer look. Believe it or not, planets are not always perfectly round. Sometimes they can have a little bulge in the middle. The biggest planets in our solar system have the biggest bulges. Jupiter, Saturn, Uranus, and Neptune are called gas giant planets, not just because they're giant compared to the Earth, but because they're made mostly of gas and liquid. Imagine a whole planet that's a huge drip floating in space. Gravity is trying to pull it together into a ball, but a big planet like Jupiter turns very quickly, twice as fast as the Earth. And when liquids spin around, something interesting happens to them. It works something like this. I've got some colored liquid in the bottom of this container. Now watch what happens when I give the container a spin. You can see how the liquid starts to crawl up the sides. It's trying to get away from the center, working against gravity and bulging out towards the middle. So all of our gas giant planets in the solar system bulge in the middle because of their spin. If you look at pictures of these planets and measure their size with a ruler, you'll see that the planets are wider than they are tall. The Earth has a bit of a bulge in its center too, but not as much because our planet is made of rock, not gas. So, the really big planets are not perfectly round. The funny thing is, really tiny worlds are even less round. Smaller objects come in all kinds of different shapes. Phobos, a moon of Mars, looks like a potato. This nucleus of a comet looks like a dog bone. And one moon of Saturn is flat like a hamburger meat patty. Eros is an asteroid that's shaped like a peanut. All of these objects are less than 100 kilometers across. And when something is that small, there's not very much gravity pulling towards its center. So it's not strong enough to smooth the object down into a ball. These odd-shaped little moons and asteroids could be pieces that were chipped off larger bodies or stuff that just never formed into a big moon or a planet.
So there are things things, even in space, that aren't round, like asteroids and the cores of comets. And some of them look like that kind of peanut shape that I showed you before. But now let's change the scale. We're not talking about something which is 10,000 kilometers across or 1,000,000 kilometers across, like a planet or a sun. We're talking about something which is maybe a few kilometers across. And now the force of the rock and the ice is dominating over the force of gravity. So gravity just isn't strong enough to squeeze in these parts and make it round. And so that's why you have anything that's upwards of maybe a few tens of kilometers across can retain whatever its irregular natural shape was. But once you get up to things that are maybe 100 kilometers or more, then gravity takes over, and gravity is inexorable. And so once you get to that size scale, the natural shape for bodies in the universe is round.
But here's the weirdest moon of all. It's called Miranda, and it goes around the planet Uranus. It's pretty round today, but scientists believe it hasn't always been that way. If we could fly over Miranda, we'd see a bizarre landscape with jagged cliffs made of solid ice. Other areas look like plowed fields, and one feature even looks like a big letter L. Scientists now believe that Miranda was hit by another object and broken into pieces. The pieces flew off in all directions, but there was just enough gravity among all of them to pull them back together again. When the moon reformed, the pieces were all jumbled up, producing this weird surface that we see today. Not too long ago, a robot spacecraft landed on a very weird world called Eros. It's an asteroid that's shaped like a peanut, and it's only about 33 kilometers from one end to the other. Now, it'd be really strange standing on one of these small bodies because they're so tiny, they don't have very much gravity. So you don't weigh very much. That means that your body would weigh, as much as a piece of paper. And every step you take would make you float off the ground. Well, that means you could have a great time with some sports, like, badminton. I mean, even just hitting the bird straight up, like this, would make the bird go up, maybe a kilometer before it comes back down again. So that means you could have a very interesting game with your partner who would actually be out of sight on the other side of the asteroid. So all you need to do is to take a good shot. It'll take about 10 minutes for the bird to make it all the way around to the other side, but if you hit it just right, your partner will get it and shoot it back. Then 10 minutes after that, the bird should come back to you. Whoa! Imagine orbital badminton. Now, if you don't have a partner, you can play badminton all by yourself. All you need to do this time is hit it a little bit harder. So about 20 minutes later, look in the opposite direction and your bird should come right back to you. Point. Gravity seems to be everywhere in space, but there are a few places where it almost seems to disappear. And it's in one of these places that a new telescope now under construction will be placed. They're called Lagrange points, and they're regions of space where the gravity of the Earth, Moon, and the Sun all balance each other out. It's like a tug-of-war where no one wins. When a spacecraft is placed at one of these Lagrange points, it'll stay right there. It's a gravitational no man's land. The new James Webb Space Telescope will be placed at a Lagrange point about 1.5 million kilometers away from the Earth. That's 4 times as far away as the Moon. Once it's out there, it'll have the clearest view of the universe of any space telescope, free from the glaring light of planet Earth. It's hoped that this new telescope will be able to see further into space than ever before, beyond all the planets, even beyond all the galaxies, out to the very edge of the universe. Finally, we should get a complete map of what our universe looks like. And the strange thing about looking out into space is that you're also looking back in time. Who knows? Maybe we'll even be able to see right back to the beginning of time. I wonder what that'll look like. Here's a way that you can see the round shape of the Earth with your own eyes. Every once in a while, the Moon passes through the Earth's shadow in space. Now, we don't normally see that shadow because space is black and it doesn't show up. But when the moon passes through it, we see a total lunar eclipse, or an eclipse of the moon. They only happen every few years, and they're usually announced on the news. If you do catch an eclipse of the moon, you will see the Earth's shadow moving across the moon's bright face. But look closely, and you'll see that the edge of the shadow is curved. It's not straight. Ancient sky watchers studied lunar eclipses and realized that the Earth must be round because of the way its shadow looks on the moon during an eclipse. Gravity is a very mysterious force. Everything in the universe is affected by it, yet you can't see it. And it does a lot more than make planets round. It seems to make space itself round as well. If space is empty, there seems to be no gravity at all. But as soon as you put in an object, it doesn't matter what that object's made of, gravity appears. And the bigger the object is, the more gravity you have. Our sun and all the planets started out as one gigantic cloud. Gravity pulled it towards its center. The cloud spun around, broke into pieces. The biggest piece became our sun in the center, and the smaller pieces became the planets and the moons. That cloud has long since blown away, but our Earth is still being pulled towards the center of the system as though the cloud is still there. It's as though space itself has somehow been curved, and we're roaring around on the sides of a big invisible bowl. Well, here's a model of space and gravity that you can make yourself using some fairly simple materials. It's the garbage can gravity well. So what you need first is a garbage can. The bigger the better, but make sure that it has a round top. Then you need a garbage bag, and Patrick has one here. And we're just going to stretch that over the top of the garbage can. Okay, stretch that over nice. And next, you need some balls of different sizes, and Victoria has a couple of ping pong balls here and a tennis ball. You can use a baseball, marbles, but just make sure they're all different sizes. And finally, this is the most important part, Rebecca is making a chain of elastic bands. And if you show us how you do that, it's actually quite easy. You just string them all together until you get a chain. And I think you're almost finished there. Is this one? And eventually what you want to get, which Rebecca has done for us here, is to make a loop of elastic bands like this. And this is going to hold our garbage bag over the top of the garbage can. So we just go around like that, okay? And then you want to pull it so that it's nice and smooth and flat, just like a drum. Here we are. Now, this represents space. And objects fly around in space. Now, if you just have one, let's start with the ping pong balls here. Okay, everybody take one. Let's just take one object, and Rebecca, let's use yours. If one object moves through space, watch what happens. Okay, make it go. Up, whoa. You can see it moves. Get ready to catch. One object moves in a straight line. Okay, you try it, Patrick. Faster than that. Objects by themselves want to move in straight lines. You can also see, okay, Victoria, put your ball in the middle, that it makes a little bit of a dent in the plastic. Not much, but it makes just a little bit of a dent. That represents its gravity. Now, the ping pong ball isn't doing very much because it's not very heavy. But let's put the tennis ball in there. Whoa. More massive objects make a bigger dent in this gravity well, and that's the way gravity works. The more mass you have, the more pull you have. Now, let's take our balls that used to go in straight lines, and let's just take one first. Okay, so Rebecca, do it again. This time, whoop, don't hit it. See if you can go by the object without hitting it. Whoa, you see that? Look carefully, do it again. It doesn't go in a straight line. It's following a curve. Try it one more time. Woo! It's following a curve because the gravity of that big object is affecting the path of this one and pulling it towards it a little bit. So if you just fly by a big object, your path will be curved. Now, here's something else that happens with gravity. Okay, everybody hold on to their balls. Put it right by the edge, and all you need to do is just let them go. And they all gather in the center. They fall down. And that's because gravity is always pulling towards the center, as we saw before. Can you try it one more time? They all fall towards. And if you try to jump up when you're sitting in your chair and you get up and you want to jump up, you go up, you fall back down. Things that go up come back down because gravity is always pulling towards the center. Now, if you can do one other thing. Okay, everybody hold on to their balls one more time. Now, if you're moving past a massive object and you don't hit it and you don't keep on going, here's something else that will happen. You will go into orbit around it. Now, let's see if we can make these balls orbit around and make a solar system. Go ahead. Ooh, this is tricky. You got to get the speed just right. There we go. Now, it's a good thing that we're not rolling around the sun on a piece of plastic because we'd fall into the center. But this is the principle that keeps the Earth going around the sun, keeps the moon going around the Earth, and keeps satellites going around us. It's called gravity. Okay, let's see if we can make a solar system here. Keep going. Our whole solar system works this way. Small objects going around big ones. The sun is the biggest of all, thousands of times bigger than all the planets put together. So it has the most gravity, and all the little planets are caught, circling endlessly around it. At the same time, moons are smaller than planets, so they loop around the planets as the planets loop around the sun. It's enough to make you dizzy.
In some sense, everything isn't round. I mean, stars are round, planets are round, but all galaxies aren't round. And clusters of galaxies aren't necessarily round. And that's because there is also momentum in the universe. Things are spinning around. And so galaxies, which are made up of hundreds of billions of stars, they're all orbiting around a common center. Gravity is still working, but gravity now can't mold that stuff into a sphere because those individual stars have too much momentum. They're whipping around in an orbit, just like if you were having a weight at the end of a string and swinging it around. They'd like to go in towards the center, but their own momentum is keeping them there. They're constantly falling. They're trying to fall towards the center, just like a satellite in orbit around the Earth. They just keep missing. And so those kind of flattened spiral galaxy shapes that you see are another natural construct of gravity. And if those things didn't have orbits, then they would, in fact, collapse down into spherical objects. So that's another way in which gravity manifests itself. And that also can happen with planets, if planets are still fluid. Say the giant planets in our solar system, like Jupiter and Saturn, they're not solid, they're made up of gas. You know, if you tried to land on the surface, what looks like the surface of Jupiter, it really would be one giant leap for mankind, because you just continue to sink through the clouds and be crushed by the tremendous pressure. And Jupiter spins very fast, about once every 10 hours. So it's spinning fast enough that its equator gets thrown out a little more than its poles, and it actually is a bit flattened. If you look carefully at a picture of Jupiter, or a picture of Saturn, you'll see that they're not quite spherical. They're kind of flattened out. And that's because they're spinning. If they weren't spinning, they'd be almost perfect spheres. That rotation flattens them out, means they have a bulge at the equator. And again, bulges are very common in the universe. I have one, again, not due to gravity, but we see the same kind of phenomena again and again at almost every scale, from the tiniest things in the universe, and for an astronomer, a planet is a pretty tiny thing, to clusters of galaxies, the largest scales, things that are big, even to astronomers.
Ooh, not bad. Well, our little solar system is coming along fairly well here. But you notice that every now and then, if you don't get the speed just right, your ball will fly off the edge out into space. That's called escape, and it's not really a bad thing, especially if you want to go from one planet to another, or from the Earth to the moon. And we just happen to have another planet here. Dallas, do you want to bring in that other garbage can? Here we have another garbage can gravity well, and we have another planet. Now, if you want to go from one planet to another, here's what you have to do. You have to escape this gravity well and be captured by that one. But you don't want to go too fast or you'll skip off into space. So let's see if we can do that. Patrick, see if you can go from here to there without falling off the edge. Too fast. Almost. That's the kind of thing we need to do. So if you're going from one planet to another, it's not just a matter of going from here to there. You got to think about what gravity's doing to you along the way. And it's not as easy as you think. Getting from one planet to another involves the gravity of the Earth, the planet you're going to, and the gravity of the Sun. Now, you start out in orbit around the Earth. Then you speed up to escape, and you head out to another planet. But all along the way, the Sun is pulling you in towards its center. So your spacecraft follows a curved path through space that bends towards the Sun. Then, once you reach the other planet, you are captured by its gravity and you go into orbit there. It's a very complicated path, and it's all shaped by gravity. No matter how far we travel in space, we're always being pulled somehow by gravity. It might be the gravity of a planet, a star, or a whole galaxy of stars. You might think there's no gravity in space, but gravity is everywhere, and it's always trying to make things round. So, what is the roundest of the round? Well, that would have to be a black hole. These bizarre objects have so much gravity, it's crushed them down into super dense balls of matter that are unimaginably smooth and hard. A black hole is black because nothing can jump off its surface. Not even light. They really are holes in space. You don't want to get too close to one of these because you'll never get out. If you did manage to stand on a black hole and you shone a flashlight upwards, the beam would curve back down to the ground, and you'd be flattened, thinner than an atom. Here, gravity is king, and nothing, not the spin, not a spaceship, could rise up off the perfectly round black hole. You know, this model of space that we saw at the beginning of the program is actually a model of a black hole, something you could fall into in space. Think you guys would like to fall into a black hole? No. Don't fall into any kind of hole. But if you were to go into space and you came close to a black hole, here's what would happen to you. You start to go around and around, and the black hole's gravity would cause you to speed up and go faster and faster and faster until you reach the speed of light. And Einstein told us that if you go faster than the speed of light, you leave this universe. So if you fall into a black hole, you don't come back. I don't think that's a place we want to go, right? So remember, gravity pulls you down. It tries to make you round, and it keeps you stuck right here on the ground. But you know something? Even though it's this mysterious force, nobody actually knows how it works. We haven't figured gravity out. Maybe one of you will be the ones to do that. Or maybe one of you will figure out how gravity works. Because if we did know how gravity works, we could turn it off. Wouldn't that be neat? Yeah. Turn off gravity. We could just float around like Superman or Peter Pan because we wouldn't have gravity to bother us. But we can't do that because nobody's actually figured it out. So in the meantime, if you want to go anywhere in space, you got to turn your back on gravity and keep your heads up.